someone keep the time for me. Do you want to do, here, I'll give you my own. Would you like to be my timekeeper?
Yes.
Oh, you have time? Do you have a, could you do the timekeeping for me? Thank you, just for me, and I'll do the timekeeping for everyone.
10 minutes.
Okay.
No, sit in front. Yeah.
Okay.
Let me get.
All right, so you.
I stand.
Okay, as everybody knows the rules, we go, you either have a 20-minute slot or you have a 45-minute slot. One of our speakers will have a 45-minute slot. So here's mine, okay? So, okay. Let me just get this up here. That's my other speech, okay. I'm so sorry, but excuse me. I'm trying to find what's this up. Oh, here it is. Okay, so here we have, okay, so this is going to be Euler, Rodrigues, Euler, and Hamilton, the problem of rotations. So Hamilton discovered Quaternions in 1843, as many of us will know, and he went through a long study and struggle to come up with Quaternions, and mainly his struggle was algebraic. But shortly after he made his great breakthrough, he found that he could describe rotations by Quaternions. The geometrical discovery was eventually published in 1850 under the title On Quaternions and the Rotation of a Solid Body in the Proceedings of the Royal Irish Academy. But Hamilton wasn't the only one, nor the first one, to think about rotations about a fixed center. Leonard Euler, Olin Rodrigues, amongst others, thought about them. In 1840, Olin Rodrigues published his paper on rotations. Now, my French isn't very good, so I'm going to ask Lucio to read this for me, my colleague. So he'll read the French. Could you read the French? Okay, should I try to read it? Des notes géométriques résistant, le displacement d'un système solide dans l'espace et de la variation des coordinates prevented des displacements considerés independent des causes prevented les produire. In Louisville, now I know that was awful. Don't say anything. It's horrible. Okay. All right. It was published in the Louisville Journal of Mathematics. So to make everybody's life easier, guess what I did? This much I can do. Translate it into English. So it's on the laws of geometry that control the displacements of a solid system in space and the variation of coordinates producing this displacement considered independently of any causes that produce it. This paper has not been translated into English to my knowledge. If anybody knows of an English translation, I would be really grateful. So we had to struggle with it in French. Okay, so Rodrigues' paper was important for several reasons. He departed from Euler by considering only the geometry of motions, kinematics, without any regard to the physics that produced it. So he wasn't worried about things like the forces, etc. Secondly, he describes general motion as a composition of rotations and translations. By doing this, he showed these combinations form a non-commutative proof, and this was something revolutionary at that time. He preceded Hamilton's formula for the biquaternionic description of rotations by 3 years before Hamilton discovered quaternions. And he introduced a set of parameters which rotations can be calculated by purely rational operators. And this is something that even Rodrigues himself said in his paper, that he did not believe that anyone else had done this. And this has become indispensable to present-day computer programmers. And does anybody know why?
Okay, well the reason is computers don't like to do things like square roots. Computers like to do addition, subtraction, multiplication, and division, and that's it. So if you add in anything more complicated than that, then computers start to slow down, and that makes computer programmers uncomfortable. So Rodrigues, and he even said it in his paper, which we translated from the French, that I believe this is the first time it has been done this way. Okay, in the course of his paper, Rodrigues supplied a proof with the theorem of Euler on motions in 3 dimensions with a fixed point. So Rodrigues' proof is essentially Euler's, but in Euler's proof, it surrounds itself with other materials, such as what we know today called Euler's angles. So if you look at the proof by Euler, and there is an English translation of this from the Latin, you'll see not only is there the fixed point theorem, but there's a lot of other stuff. Okay. We shall use modern vector notation to describe Rodrigues' composition theorem for pure Quaternions about an arbitrary origin of coordinate O. Now the reason we're doing this, of course, we're more familiar with the language of vectors than we are familiar with the language that Rodrigues used. I mean, Rodrigues used tools like projective geometry and things like that that people in his day were very familiar with, but we are not as familiar with. So to make things a little easier to understand, we translated it into modern language. So let alpha L hat mean the rotation about the axis L hat. So we have these axes. Let beta M hat mean the rotation through angle about axis M, and let gamma N hat mean the rotation through the angle about axis N. So Rodrigues was able to prove that the composition law, we will say, is gamma N equal to alpha L hat beta M hat. So, and this is equivalent, so after much calculation, we found that it's equivalent to this, where he uses the half angle cosine gamma over 2 is equal to cosine alpha over 2, cosine beta over 2, minus the dot product. Of course, he didn't know dot product, but essentially he did the same thing, or equivalent to what we would call a dot product, L dot M hat sine alpha over 2, beta over 2. And similarly, for the vector, where he does something very similar to the cross product, even though he did not know it was called cross product, and came up with something similar to sine gamma and N hat sine alpha over 2, beta over 2, L hat, etc., etc. Should I, okay? So this is the other part. So these are the same formulas that arise from multiplication of 2 quaternions. So we decided to test this, okay? So what we did was we took, let the quaternion be with scalar and vector part, cosine alpha over 2. And this is as Familton. If you looked at Hamilton's 1850 paper, you'll see that Familton did also use these half angles. So cosine alpha over 2, L hat sine alpha over 2. Okay, similarly for QM, cosine, we'll say is beta over 2, M hat sine beta over 2. M hat sine beta over 2, and then similarly for N and cosine, Q of N, cosine gamma over 2, sine hat N sine gamma over 2. So, and then of course we just have here, and we decide, okay, now we have the formula, and we just, we do the product, and we just simply calculate it out. So here, working it out, just plugging it in, the definitions, and then using commutative laws, just commuting, going through the whole commuting process, and then we find, guess what? We got the same formula, okay, using Quaternions. Whether we use Rodrigues' way of looking at it, or whether we use the Quaternionic way of looking at it, we end up with the same relationships. So, which is the same formula, same as Rodrigues, but without quaternions. So we did it both ways. We looked at it both ways. So again, using modern, so what Hamilton did, now we're going to try to go into what Hamilton did. And this is again based on Hamilton's, and we're going to use modern notation. Okay, we derived a biquaternionic formula for rotation, because Hamilton used what was called biquaternions. And so we give it a unit vector n, and n in 3 space and an angle theta. And we want a formula that can be applied to any vector v to obtain the result of rotating v through n to angle theta. So we're going to call the result v prime, the vector v prime. So we'll say for any vector w, we shall write w bracket for the quaternion. So we use our usual quaternion definition, IWX plus JWY plus KWZ.
No, it's 20 minutes.
And then we just multiply out. Okay, so we have W and W prime, and then we just multiply it through using distributive law, and we get this relationship. This was not that simple, believe it or not, okay? And this is one of the things I learned about when using quaternions. This took us a long time to do. I mean, it looks nice when it's all written out, but after we had to struggle through it a long time to get it to work out because of all the confusion about the sign, you know, the signs and everything like that. Okay, I got a bad number, wait a second. Okay, I don't know who that is. I just got a robocall, sorry about that. I apologize for that. So this took us a while to work out, to get everything to work out nicely. And then in particular, okay, we have n hat v is equal to negative n hat v plus n hat cross v. And similarly, okay, for v n hat minus n hat, v n hat plus v across n hat. So we're going to keep in mind for the future that if we put these two together, the dot product, the first part cancels out, and we end up with 2 n hat cross v. So now we're going to let w, and here we go back to our w, and we're going to let w equal to n hat cross v, and w prime equal n hat, I think there's a mistake, n hat in 1, okay? So we have, okay, so we put them together. I think there's a little mistake here. Okay, so we put them together and we do the whole process. Again, these working with quaternions directly, the biquaternions, was not a trivial process. That's why one can understand why Gibbs ended up and Heaviside ended up modifying quaternions, because they are not easy to work with when it comes to calculations. And as I said, my colleague and I, we learned this the hard way. Okay, so replacing v in 3 by nv and given 2. So we go back, and there we have, and again, this was not that much fun. Okay, so we got negative nv, okay, this formula, and then we have v minus 2n minus vn. So all we're doing is taking our results and plugging it into the rotation formulas. So now, given theta and n hat, we now form the unit quaternion. And this is something that in Hamilton's paper, Hamilton actually discusses this and talks about these things in his 1850 paper. So we're going to use this relationship, and we're going to use its conjugate. So we're going to take Q and Q star. So we made the conjugate, 7 and its conjugate, and then we propose the rotation formula. So we propose V is equal to Q, V prime is equal to Q, V, Q prime. So we have now, guess what? Plugging everything in and working it out, starting to look a little bit familiar. And so we go through this whole big calculation. Again, working with quaternions can be directly with quaternions can be very, very nasty, as you could see. And we finally, using 4 and 6, this becomes QV, Q star, and we have there, we plug them in, working it out, okay? So finally, after working on using our trigonometric relationships, etc., substituting all your basic trigonometry things, we recover the formula for V prime. And this formula, V prime is equal to V prime cosine theta plus n hat cross V prime sine theta plus n hat, V, n hat, and then V hat dot V prime times 1 minus cosine theta. This is known, if you've read papers and you look at papers, this is known as the well-known Rodrigues rotation formula that Rodrigues found by direct geometric arguments. So we come to the conclusion, after going through all of these things, that you can go back and forth between whether you're looking at it from Rodrigues' point of view or whether you're looking at it from Hamilton's point of view, they come out to be the same thing. So, Rodrigues is concerned, Hamilton and Rodrigues. So Rodrigues' concerns with geometric and analytical mechanics. Rodrigues did everything in the real field. He did not even consider complex numbers when working out his calculations. Rodrigues and Hamilton came to the same conclusions about rotations, but they took very different paths. As I showed you, and as my colleague, we showed you, that even though they took different paths, at the end, the same formulas ended up coming out. And they say exactly the same things. However, they both arrived in a common place using half-angle formulas. So that was the real revolutionary thing that the two of them did that had not been seen before, is using half angles. And this is something that Cayley made a note to. So in 1846, Cayley acknowledges Euler's and Rodrigues' priority in describing orthogonal transformations. These are just regular transformations. In the letter to the editors of Philosophical Magazine Journal 13, he wrote on certain results relating to quaternions. Cayley credits Rodrigues with his use of half angles in his transformations. Cayley refers to Rodrigues' 1840 paper, mentioning that Rodrigues' results were equivalent to Hamilton's quaternions. So it turns out that even though Rodrigues was not a well-known mathematician in his day, he did something really, really extraordinary given the times he was living in. And the thing is that this was something that was really very, very interesting, and a lot of people were thinking about at that time, because as I mentioned earlier, Euler, Hamilton, Rodrigues were not the only people to think about rotations or things that are related to these rotational products. So here is a timeline, and I did a timeline here, 1840 to 1845, that includes some other people who contributed to the subject besides Gauss. Everybody knows Gauss did everything. So, of course, didn't publish it, but we know he did everything. So I left out Gauss. Okay, so in 1840, Rodrigues was 46, and he wrote his kinematic description of solid movements, which is what we just talked about. And then Grossman, which I spoke about yesterday, in 1840, he was 31. He did the theory of tides, and he presented this, but it never got properly published. Hamilton, he was 38. He did the algebra of quaternions that we all know and love. And then in 1844, he announced about the biquaternionic rotations to the Irish Royal Society, but didn't publish it until 1850. In 1844, Grossman was 34. He published his linear theory, his theory of linear extensions, which is his most famous book, where he talks about the exterior product. In 1844, Eisenstein, talks about non-commutativity of linear transformations. And non-commutativity, as you know, is important in these rotations. So the fact that we're talking about non-commutativity is important. And then in 1844, Boole, who was 29, he wrote his first paper on symbolic algebra, meaning that you can use symbols for something more than just numbers. You can use them to represent objects. And then in 1845, Cauchy, who was 56, wrote about the non-commutativity of permutations, again, important in the rotation theory. And lastly, Cayley at 24 wrote about 2 by 2 by 2 hyperdeterminants, which also became important. Okay, so thank you very, very much.
Thank you.
And I hope you enjoy it, and here is my colleague. If you have anything to add, Lucio, to what I did. After everything we talked about.
So what is true really are the formulas, right, to make the connections in modern way. So this takes time, and the test is also in French, so it's another hurdle to separate. But, in the end, you are capable to resolve the situation.
So we managed to tease it apart and try to bring it back together
So
again.
I think for the next year, I think is to discuss is to make the relation, the notation you just use here about the cross product, that product that gives the later. So you're looking in the historical context in a way to you see very well neat, concise way to explain the ideas. But geometrically, it's easy to understand because in old fashion, they have no picture in Rodrigues' paper.
None, right? We had a.
So everything is written. So they say the geometry I described in the previous section, blah 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 blah. So it's very hard to understand. Yeah, from there he wrote the formula. So you need to interpret in this because you don't have any specific figure in there as in modern. So that was the hurdle.
Yeah, we had I was just showing the audience here, remember, here's the paper, and there are absolutely no pictures, and I know I saw Lucio's copy, he was drawing all kinds, and you can see me, I'm drawing, or trying to understand it, not only reading the French, but we were also trying to figure, out how to represent it pictorially, because we're talking about rotations and angles, which gives itself naturally to pictures. And I forgot my pipe cleaner, my models, but I made actually models with pipe cleaners. And
I add one more point here, is that he is not only concerned with the geometry, but also the mechanics.
Yeah,
so
the analytical
this is a
mechanics.
mixing there. He points out in the paper, he say there's a big difference technically. It's not on the mathematics, but the way you approach everything there.
The
so in
kinematics,
Hamilton
right.
is more oriented to the algebra, take as a reference the complex numbers. That's all.
Exactly. Okay, any questions for either of us about this? Yes.
I was really interested to see in your list at the end there, you mentioned a paper of Eisenstein from 1844.
Right, yes.
So in 1844, Eisenstein published an unbelievable number of papers.
I know that you had a big
something
explosion.
like 20 or 25. I can't imagine anybody who's ever published as many papers in 1 year as Eisenstein published in 1844. So I'm curious, do you know in what context, in what paper and context Eisenstein
I just
mentioned
sort of
this?
put this together at the very last minute, thinking, oh, this is kind of interesting in the paper, from the papers that I read. But I could look this, if you want to email me, I can look this stuff up and tell you which paper this actually came from. Because even Gauss was saying, the three greatest mathematicians, and he said, well, Archimedes, Newton, and Eisenstein. So if Gauss gave Eisenstein such high praise, and it was really sad because he also, Clifford died rather young from tuberculosis, and it seems like tuberculosis, now we've cured it, but was one of the really, really bad things that killed a lot of potentially great mathematicians. But I can look at that. Yes?
I just want to comment, maybe it's time to translate.
Yeah, well, I think we're actually somehow doing that,
Yeah.
whether we like it or not. I mean, loosely,
Yeah,
we're actually sitting here, we've been
You are
plodding
forced
through this,
to make,
through this, and.
you know, you have a Google translation now. Is
Yeah,
that
well, yeah,
helpful?
we do, I do count, that
Is that
sounds like
something
my way
that
of
help
combination
you
of
to
Google
look in the
translation
originals,
and my
something?
graduate school, yeah.
Yeah, that's something to help with also. But you know, it's a good suggestion.
Yeah, that's my way.
Because
of doing it.
Euler, for example, you have in
Right,
Latin,
yes,
You
right,
have the
right.
very good translation from Latin.
Actually, it's quite easy to do now, you just hand it to Google Translate.
Yeah.
Well, you have to know what you're doing. I know, you have to know some French, and you have to know some German to
It's
do
about-
it.
Of course, there are also plenty of people who can translate French.
Okay, that's.
I think I would undertake it if people wanted.
Yeah, I'm just surprised that there is no, I was there, we looked, we couldn't find one, an English translation, so we just, with me, it's Google Translator and knowing graduate school French. I mean, that's what I use.
Yeah,
And the same thing with, when I was translating Rossmann, I used Google Translator and graduate school German, so. Any other questions or comments? Okay, thank you very much.
Thank you.
Okay, thank you, Lucio. Okay,